All right, welcome everyone to the session for System Analysis and Emerging Challenges. I am Amir from Rice Research Institute of Sweden, and I have a pleasure to chair this session. And the first presentation is about life cycle sustainability assessment of photo-activated process for CO2 reduction and fuel production from lab data into industrial scale by Valva. Please.
Is there any microphone?
No, the microphone is already integrated, but you can use this pointer if you need, just to change the lights. I think the pointer doesn't really work on the screen.
You can maybe use to change the slides.
Just to check. Yes. Yes.
Hello, everybody. I'm from Himna Energy Research Center, and as part of the design project, I'm going to have a presentation about the life cycle sustainability assessment of it's a study for producing for CO2 reduction, photo-activated process for CO2 reduction and fuel production. Actually, here we are talking about sustainability in many projects, and in many cases we claim about more sustainable technologies, products or systems. But the question is that is this sustainability measurable, and can we specify some indicators to tell us that one technology is more sustainable than the other one? So here we follow an approach. The name is life cycle sustainability approach to answer this question, how we can measure the sustainability of new technologies and products. In this approach, we apply life cycle thinking technique that actually in this technique we consider the full life cycle stages of a technology, starting from the extraction of the raw materials to the manufacturing of the devices and processes, then to use phase, and finally to the end of life recycling to close a loop in the life cycle of the technology or product. So by this way, we avoid shifting the burdens from one life cycle stage to another life cycle stage. So by covering the full life cycle of a technology, we can avoid this shifting of the burdens from one stage to another stage. And the definition that we have for sustainability in this approach is considering three different aspects for sustainability. One is environment, the other one is economy, and finally the society. So by considering these three pillars of sustainability, we can, and also this life cycle stage that we have, and different indicators in each of these sectors, we can cover the full impacts of a technology or a process that is going to make in future. So here I'm going to present this case study for a photoelectrochemical system that actually here we have a kind of photoreactor. That is, photoreactor has a composite structure. We have a photocathode on one side of the reactor. On the other side, we have the anode, and a membrane, a proton exchange membrane, is making the difference, like in the middle will separate these two parts of the system. And additionally, we have some other components, some metallic components, plastic components, and gasket and sealant component to have this full structure of the photoelectrochemical reactor. In this photoelectrochemical reactor is getting wastewater from one side, and the water will be treated, and treated water will be leaving this anode side of the reactor. And on the other side, we have CO2, and the CO2 will be reduced to some fuels. At the same time, this system is a hybrid system, and it's able to operate under two different operational modes. One is the photoelectrochemical mode, and the other one is electrochemical mode. The difference is when we are working in photoelectrochemical mode, it's need to get light from the sun, so the availability of the system is limited to the sunlight. But when you change it to the electrochemical, by getting some extra electricity from the grid, it's able to keep the operation of the system. So it gives us a full availability. So for any kind of life cycle assessment, life cycle sustainability assessment, we need to define the system, and we define it with the system boundaries. So in this case, we have two different system boundaries. One for the manufacturing of the photoelectrochemical reactor, and the other one for the operation stage. In this system boundaries, we have inside the boundary, we have all the activities and processes that you need to produce or to manufacture the photoelectrochemical in this one, and in the other one, any kind of activities, processes, and system that we need to operate the system. And this system boundary is showing the interaction between the foreground and the background processes by the material and the energy that we need to provide to our system, first to manufacture the photoelectrochemical reactor, and the second to operate this one, to treat wastewater and to produce fuels, and then making purification of the fuels. So as we have the system defined, we need to develop the life cycle inventory. This life cycle inventory actually is the material consumption, the energy consumption, and any kind of utility that you need to first to manufacture and then to operate the system. So to get this inventory, we did several modeling approach to provide this data based on a large-scale application, large-scale manufacturing, and real application of the system. So the first model here is a model that we call it Design for Manufacturing and Assembly, DFMA model, that we applied this model to consider a large-scale manufacturing of this device that we have here. And actually here, it's kind of a big factory that is based on the breakdown structure of the system. We have different sub-processes to produce the different pieces or different components of the system. And then when we have this large-scale manufacturing of these components, we get them together in some sequential assembly steps to have the final product. So for example, here in this photoelectrochemical reactor, we have some plastic parts, photoanode, photocathode, the anode, the membrane, gasket, metallic part, and tensioning system. And each part is completely separately is produced at large scales and then assembled together to have the final product. So this DFA model is very critical to us to have the detail of the manufacturing process at large scale. When I'm talking about large scale, I mean like 10,000, 5,000 photoreactor to be produced annually. And another approach of modeling that we applied is for the operation stage. So in this case, we are considering implementing these photoelectrochemical reactors in some real wastewater treatment plants to treat water and then produce fuel. So we are considering kind of grid configuration for these photoelectrochemical reactors to be installed in this wastewater treatment plant. So like thousands of these photoelectrochemical reactors will be installed in this configuration. And we have some number of photoelectrochemical reactors in series to provide the residence time of the photoelectrochemical reactor to complete the reactions, the CO2 reduction reaction, and also the removal of the pollutants. So based on the residence time that we need to complete this reaction, we multiply the number of the photoelectrochemical reactors. And also depending on the flow rate of the plant, we have several rows of these photoelectrochemical reactors to provide the full scale or the full capacity of the plant. So actually, I mean, here this is residence time is very critical to us to know how much time we need to complete the reactions to determine the number of the reactors. That by itself is not a constant parameter. It's a function of the current density and also the feed flow rate of the plant. So the flow rate that you get to each row of this photoelectrochemical reactor. So we need to do some modeling using some experimental data to correlate the relationship between the residence time, the current density, the flow rate, and everything to have a Aspen Plus model that we have here for the operation. In this Aspen Plus model, we have this modeling parameters, the equations, and then all the data that we have to have this continuous process. That actually here we have the reactor. We separately simulated or modeled the anode side and also the cathode side as two different reactors. We have the membrane in the middle. So we have the wastewater getting into the anode side, the CO2 with some catholyte will go to the cathode side. So the reactions happen and some product will be produced. And in this case, the product is a syngas stream mixture of CO2 and hydrogen. This syngas stream then to complete the reaction, like the process, to have a single product, we apply the water gas shift reactor here to convert the carbon monoxide to more hydrogen, to get hydrogen as the final product of our system. So to do this one, we did this integration in the process, and also we have some purification parts using PSA unit to purify hydrogen and then compressing hydrogen to desired pressure. And some like off gases will be again used for making some heat to be used in the process. So anyway, this is Aspen Plus simulation is providing very critical information and data to evaluate the sustainability of our technology at large scale processes and in a continuous process. So by having this modeling activities, we get the result. So I'm presenting the results based on the different indicators that we have for sustainability, economic, social, and environment. The first is life cycle costing result that more or less is the same as techno-economic assessment result. For example, here for the manufacturing stage, we have the cost of manufacturing for this photoelectrochemical reactor that you see by increasing the annual manufacturing rate from 500 to 10,000. The price is reducing, is sharply reducing. Like so, for example, here you see that when we have small scale of manufacturing for these photoelectrochemical reactors, the capital cost is the main contributor to the total cost of the reactor. But when you increase the annual manufacturing rate, the material cost will be the main contributor. So it's showing the economy of scale on this large scale manufacturing of the photoelectrochemical reactors. And also on the other graph here, you see this hotspot identification. Like we have this breakdown structure of the photoelectrochemical reactor, the metallic part, the plastic parts, the gasket membrane, photocathode, anode, and etc. So you see how these components are contributing to the final price of the photoelectrochemical reactor. So it's very critical to know these details to identify the hotspot, which component is making the highest contribution to the price, and how the increasing the annual manufacturing rate of the photoelectrochemical reactor will change the price. And when we move to the operation, we have this result for the cost of hydrogen as the final product. So when we are talking about the operation, as I told you in the beginning, that we have two modes of operation. One is photoelectrochemical mode that is actually depending on the sun. So it's 12 hours operation and 50% availability. But at the same time, you can move to electrochemical mode, and we call it the hybrid mode. So during the night time, we can provide this external electricity to keep the operation. So we have the results based on these two different modes. One is PEC mode and one is the hybrid mode. So here you see that in the hybrid mode, actually the operating cost is always more than the PEC mode. But on the when we are talking about the capital cost, the hybrid mode is cheaper than the PEC. And when this the operational cost and the capital cost is converted to the levelized cost of hydrogen, here we see some kind of like the turning point at some specific current density. The price of hydrogen produced from PEC mode is less than the one from the hybrid mode. Actually, here we are presenting this result based on the current density of our system to show how in future, if we get higher current densities, the system will change. So at the current state of the operational, at the current state of this technology, the current density is 100 ampere per meter square, but we are predicting the future advancement to get a higher current density that is 1,500. So you see, by increasing this current density, the price will decrease. And also we have this turning point between the two modes of operation. Regarding the LCA result, the environmental results, we have this graph for the manufacturing step. So in the manufacturing step, you can identify the hotspot. Actually, we have three environmental indicators: the climate change, acidification, and material use. And here you see that basically the metallic part and the anode and the photocathode are making the highest contribution to the manufacturing of the photoelectrochemical reactor as the LCA result. And more specifically, when we convert these results to the processes, the titanium production and graphene oxide production are the main contributors to the environmental impact at the manufacturing stage. But when we move to the operation, different indicators, same indicators we have, the climate change, the acidification and material use. And also we are presenting the results again for two different modes, the PEC mode and the hybrid mode, and at two different state of the technology, the current state and the future state, 100 and 1,500 ampere per meter square. So here we have the hot spots. Like actually, it's like that. Always the PEC mode is showing lower impact compared to the hybrid mode, and when by increasing the current density in future, the environmental impact will be substantially less than the current state. And also at the current state with this 100 current density, electricity and material are the main contributor, but in the future, electricity will be the main contributor to the environmental impacts. Regarding the social aspect, okay, we have same graphs for identify the hotspot. Again, metallic parts, gasket and membrane are the main contributor to the social impacts that we have. Actually, child labor, contribution to the economic development and fair salary are that indicators that we have. And also same results for the operation phase. At the operation, again, by future advancement, the social impact will be much less than the current state. And actually, electricity and photoreactor manufacturing are the main contributors to the social impacts of this technology that we have. And finally, we have a benchmarking, sustainability benchmarking, because actually we need to have a reference system to benchmark our system to know how sustainable is our system. So here we have this benchmarking against hydrogen produced from steam methane reforming as a conventional mature technology. So and by this comparison, you see here that our system at higher current density, that is something for future. At the PEC mode is showing less environmental and social impacts compared to the steam methane reforming hydrogen. But for the hybrid mode, always the indicators are more than this conventional technology that we have. But still, we have a challenge. That the challenge here is the cost of the hydrogen, the economic indicator. That in both cases, the cost of the hydrogen that the system is producing is much more than the conventional steam methane reforming. So it's showing that sustainability is not just one aspect. We consider all the aspects. Maybe in some aspects, by your new technology, we get benefits, but in others, you will have some drawbacks. Thank you for your attention.
Thank you, Wafa, for next presentation. Any question from audience? We have maybe time for one question. Yes, please.
Yes, please.
Hi, thank you for your talk. Your model is about current density parameters that in PEC mode are not feasible because the absorbent light absorbers will never reach 1 ampere per
100 ampere per meter square. Actually, experimentally, we reached when this device is showed that the experimental state we have this one.
Since you are doing per meter square, can you translate to amperes per centimeter?
0.1, I think.
It's times.
Yeah, 0.1.
0.1.
Yeah, I think.
But that's for not even solar panels reach that density.
But actually, in electrolyzers, in PEM fuses, we reach around
no,
1.
I'm talking PEC. I'm talking PEC. A solar panel doesn't reach that current density. So how can you work in PEC mode at that current density? I'm not talking electrolyzers. Electrolyzers can run much higher.
Yeah.
That's for an electrolyzer, that's very low.
Yeah.
So my question is how in PEC, pure PEC, can you reach that current
Actually,
density?
this PEC this voltage is not 100% coming from the sun, like the light. It's like 40% from the light, and another 60% is coming from some external voltage that we have, So this 100% of this 100 ampere is not coming exactly from the sun. It's a photoelectrochemical mode. Some part is from light, and the other part is from this.
So that's not the definition of photoelectrochemical. But anyway, I was just wondering how with a light absorber, can you reach these currents, because it's not visible.
Yeah, actually, it's the data from the partners, and they reported this value for the currents.
That's not an answer.
I think it's 0.01, right?
He mentioned 0.1,
No, but 100 divided by 10,000 and 0.01.
but he showed one.
100 ampere per meter square. So yeah, it's
0.01
square, not 0.1.
0.01.
0.1. Yes.
Okay, but he mentioned 0.1.
Yeah, because you need to divide by 10,000. That's why, yeah. 100 divided by
Yeah,
So it's 0.01. So
0.01.
it's just 10 milliamps per centimeter square.
Is it feasible or not?
That's not acceptable in the environment. In an electrolyzer.
So it's not the result is showing that at the current state, the
In
technology
an electrolyzer, you should run at 1 ampere per
Yeah,
centimeter square.
maybe we can continue the discussion. after
Yes,
this
but-
session.
You should give me the right.
Yeah,
But it has
but-
a simple mathematical calculation, like 100 divided by 10,000, so 0.01. Was my mistake to do.
Thank you, and maybe we can continue the discussion later. You have the contact information.
Thank you.
Thank you. Next presentation is from Dr. Jimian Hao
Yes.
from Delft University of Technology and it's about targeting electrochemical performance of methods for urea production.
Hello. Hello everyone. Thanks for the introduction. Hello everyone. I'm Jimian. I work on electrolysis for the urea production within the iconic project. So my work is mainly to identify the proper targets for the lab scale. So basically, mostly motivation behind it is because there are environmental challenge and also material supply challenge. On one hand, there are excess nitrogen on the ocean, basically can cause eutrophication issues. While on the other hand, in the EU there's there's a gap for urea imports. So basically, what our project Iconic is try to move the unwanted nitrogen to where we need the nitrogen. So basically, nitrogen fertilizer. So the Iconic, the full name is integrated conversion of nitrate and carbonate. So basically, develop a urea production technology. So basically, CO2 plus the nitrate to the urea product, and we try to reach the social, economic, and environment benefits. That's our kind of potentially, and we collaborate with several institutes, very nice institutes, including our leading partner is ICSFO, and also the collaboration in TU, PAM University in the Munich University, Technology University in Munich in Germany, and also doing in Ireland. So basically, here the research question is: are most of collaborators very smart people working on the electrolyzers, basically the device like memory and electrolyte, and also a lot of characterization techniques. And we see a lot of reports and the literatures for report the Faraday efficiency and current density. That's normally we see. And then, but the things they are not very clear. What's the targets we need to reach for those key performance indicators? So basically, that's a kind of, for example, a list of current results. Then what's the proper target for the future? And we try to answer this question in the process level. We build the kind of process model, not just for electrolyzer, but also our upstream and downstream separation. And then to compare that with conventional pathway like Haber-Bosch and Bosch-Meyer for the urea production. Then we try to compare those two technology and to see how to make this new technology economically viable and environmentally friendly. So we did a model for the electrolyzer, basically for the mass balance, and so basically you see our electrolyzers. It's not just the urea production. It's also for the nitrate reduction to the ammonia, and also for the gas phase of CO2 reduction to other product, we say the side products. So far, actually, the urea, like Friday efficiency urea, actually is not very good. So basically, in our lab, in the lab, basically we see that, for example, Friday efficiency urea is just 0.8. But we see that very good value in the literature can reach like 0.75 or like 0.90. But then we need to know like what's the proper target for that. And so we did a kind of mass balance for that. And also we did like energy consumption. In this energy consumption, we built a relationship between the cell voltage and the current density. Basically, the cell voltage related to like thermodynamics and also over potential in the cathode and the anode, and also the ohmic loss, and also with the transport limitation. And we can times by the cell voltage by the current then to get the energy consumption for the electrolyzers. And also that's just for the mass balance for the electrolyzers, but we also did a kind of process model for the ocean capture and separation in Aspen Plus. So that's the current results for the greenhouse gas emissions. You see this is emission for the urea production, like per kilo urea is like 100. And currently the dashed line, that's the conventional process like Haber-Bosch and like a Bosch-Meyer is like just 1.4 this value. So we see like lots of actual contribution come from the purification. That's because we got very dilute urea products. And if we see like what happened in this zoom in this part, we say, okay, what's the kind? You see this more clear for the dashed line of the we see like a fossil urea, like conventional urea. Then this time you may say, okay, we see like okay, if we just improve the electrolyzers performance, basically you see this is our current lab data, like 0.08 to the for the urea Friday efficiency. But if we improve that to like this column, is basically the efficiency is almost like 100%, and also conversion of nitrate CO2 is also 1. But still, we see that still cannot compete with the fossil urea. That's just for greenhouse gas emissions. We are not talking about the economic yet. The reason we found, okay, what's the reason behind is because of this urea products, the concentration is very, very low, like 0.01%. That's because of our like feedstock of the nitrate when we're doing in the lab, like this just like 0.1 more for the nitrate. And our experiment people is just like this concentration should be even lower. So this is if it's lower, and this concentration can be even lower. Okay. So okay, but we still need to solve the problem. Is we just not to point out the problem. So what we do is like we think about like we should probably add some concentrator technology for the urea, and also some heat integration technology, for example, heat pump. So this is what we do, like we add the urea concentrator technology by the reverse osmosis. So it's not just for evaporation. We can use the membrane technology, and this can reduce the energy consumption by 90%. And with the heat pump in the separation, basically for the evaporation, we can further reduce the energy consumption by another 90%. And also with following by like multi-effect evaporation and the crystallizer for the urea purification. And this time we can see like our still like 3 scenarios, like for this x-axis is basically the performance improvement direction for the electrolyzer, and the y-axis is still the greenhouse gas emissions. We see like zooming this part. This time we see okay, with the kind of RO is basically a urea concentrator. So basically this time you can see like with this urea concentrator, we can greatly reduce the greenhouse gas emissions, and also with the heat pump, that's also we reduce the purification part of energy consumption. And also this next step is we did like energy and economic analysis for this urea. So we did kind of a current density with the x-axis, and we see the operation cost. So actually, it's decreasing. Actually, that's a question I want to ask Wi-Fi. So I think the result is a bit different because from my model, it's basically with the higher current density, actually it's higher cell voltage. So basically, that's for the operating energy. Actually, it should be increasing. And but the things with the higher current density, actually, we need to like smaller electrolyte area. So basically, the capital cost can be decreasing. So this way, we see like kind of a total cost. Actually, it's kind of this kind of curve. So there's some kind of a suitable window for the current density. So we see like this value is like around like 50 to 100. But still, we see okay, that's the cost of fossil urea. So it's like here it's like 0.3. Still, we see okay, this value much higher than this value. But the things our iconic target is like €1 per kilo urea. Still, we thought okay, we can still find some window for that. And we back to our original question. Okay, what's the kind? So we see, okay, those technology upstream and downstream, we assume they are very material technology, but this electrolyzer is very low technology level. That what's the kind of lab targets? Like if we want to like economic viability and environmental viability. So that's we do it like for example, how what's the concentration we should reach for the urea concentrator? Like we set like 4 scenarios, like from 0.1 to like 2%. Basically, we say okay, without like heat pump. Basically, we say okay, this. So basically, those region will be the proper region for like Faraday efficiency and current density. So make this new technology compete with the fossil urea. So basically, you can see the region. Of course, with the higher urea concentration, of course, there we can have a flexible feasible region for the electrolyzer. And also with the heat pump, of course, this region can be further increased. So basically, you see like this way. Basically, we found okay, if we reach the urea concentration to like 1%, actually, that's a proper concentration after the urea concentrator. And we see also for sort of like what's the proper manufacturing sites for Netherlands or Spain to place this new technology. We give some 4 scenarios. The base case of basically for base scenarios, we have like higher electricity cost and higher electrolyzer cost. And for the optimistic scenarios, we give like electrolyzers cost like divided by half, and also the lower energy cost. So this time we say, okay, what if we compare this our new technology with fossil urea? For example, if we do like if we do place this new technology in the Netherlands, we find okay, this might be the feasible region to compare with the to compete regarding the greenhouse gas emissions. So basically, in the Netherlands, we have a broader feasible region for the Faraday efficiency and current density. But for the Spain, basically, we find like the window actually is very narrow. But for the economic, that's different story. Because of solar in Netherlands, we got like a very cheap wind, but that's for the solar energy in Spain is even cheaper. In that way, so basically this time we see like if we compare the economic cost, basically even for the optimal scenario, this technology still cannot reach our iconic target like €1 per kilo. But for put like in Spain, in very optimal scenarios, if we reach the current density larger than 50 and current and Faraday efficiency higher than 0.4, basically that's a feasible solution for economic viability. So back to our conclusion, what's the kind of target for the electrolyzer. So of course, the farther efficient, that's for the yield of urea. So the higher the better, but for the current density, that's something, okay, there's a proper window for the operation. And also we found another target for the electrolyzer cost should be much smaller than 5,000. Actually, this value is very challenging based on our current economic information. And also we find like downstream actually matter a lot because for that's because for the energy. That's because for this, if we must use the evaporation for the dilute urea, and of course we can consider some heat integration technology, and also another thing is like we probably need to explore some novel recovery technology for the urea, and basically now my calculation I see like it's like fully retention for the urea of this, but actually in reality urea molecule is more uncharged. It's not. It's actually not like 100% retention by the membrane. So the membrane technology actually is needed for downstream separation, and also for the manufacturing side. Of course, the Netherlands can have lower greenhouse gas emissions for this technology, but for the Spain, it's more economically viable. And that's my presentation, and I would like to thank my collaborators and also thank for your attention, and I'm open to questions, and also I got my email over there if you want to have more discussion. I'm happy to talk.
Thank you, Jimmy.
Yeah.
Any question?
Thank you very much for your talk. Very interesting. Yeah. We learn a few things, very precise. I have a curiosity, how do you, because in your case, the extraction from seawater of nitrates or these things look like cheap. Is this is this that simple? Because seawater is kind of a complex mixture.
We did that in like ocean capture from CO2. So basically, it's a technology that's kind of we use this technology. Basically, it's like per ton of CO2 is like six
For CO2, I understand,
yeah.
But for nitrates.
Nitrate, but that's a good point. I actually I didn't in my calculation I didn't include like a nitrate concentrator. So if you see my calculation, there's no nitrates.
Okay.
I haven't considered that.
Okay.
Thanks a lot.
Okay.
But let's make add the emission.
No, I understand.
Yeah.
It was a curiosity because I
Yeah.
didn't know of a process. I
Yeah,
want
yeah.
to do it.
Okay, one more question.
Yeah, then I have a question on the efficiency. How, let's say, where are the experimentalists, which efficiency, and how, let's say, easy is it to reach certain efficiency that to make this viable?
So basically, my conclusion is basically, if we for for the most simple way to improve this technology is it's basically it's for like if we just improve like further efficiency. Actually, you can see you can just reduce emission a lot.
Where are they now? I mean, the experimentalists?
Experiments now is like 0.08, but that's for our Delft results. But in the literature, they do that in like 0.75 on. Yeah, but that's we haven't repeated the result actually. For example, our collaborator challenge actually is doubting the reports value in the literature. Yeah.
Okay, thank you.
Yeah.
And move on to the next presentation. Next presentation is by Dr. Juran Divos from Vito, and is about 3D printing and preparation of catalyst monolith for Fischer tube synthesis. Actually,
Then just a second. I need to find the correct one. It's this one, I guess. Yes.
Yeah, thank you for the introduction. So indeed, as mentioned, I will be talking about 3D printing and preparation of monoliths for Fischer-Tropsch synthesis. Now you can think, okay, why 3D printing of catalysts?
I'll try again. Yes.
Okay. So why 3D printing of catalysts? Well, actually, it's being done by industry at the moment. So the technology is being scaled up. I know that BASF is currently building the TRL7 pilot for 3D printing of catalysts. So it's becoming very important also for the industry because they realize the benefits that it can bring. So now, why are these structured catalysts beneficial? Well, if you look at conventional catalyst shapes like pellets, if you want to have good geometric surface area, which actually determines the conversion reactor, you have to go to very small beads. Now, of course, if you have a reactor filled with these very small beads, you have a lot of resistance for the flow to flow through the reactor. So you have a lot of pressure drop, which is actually the energy consuming part of the reaction in that case. Now, of course, if you go to monoliths, to go to honeycombs, you can reduce the pressure drop dramatically and improve the surface area, but you don't have no mixing. So in a car exhaust catalyst, it's very interesting, but in a chemical process, it's not so efficient. So sitting somewhere between those things, you have 3D printed catalysts. So here I show, okay, if you have big pellets, you have issues with mass transfer, but to the structured catalyst, you can design it in such a way that you have a high geometric surface area, a low pressure drop, and that you can have mixing. So you have enhanced activity, selectivity, and stability if you design it well. Now, 3D printing is very broad. You have a lot of different techniques. You have techniques based on polymers. You have techniques based on lasers, on UV light, and so on. But the technique that we are using in our group is based on extrusion. And on why? Because actually it's the closest one to the catalyst industry, because they also use extrusion for their catalyst shapes. So why? It's broad. You can use different materials. You can work with MOFs. We can work with ceramics, silicon carbide, and so on. It's relatively low capex and opex, and it's a technology which can be scaled to large volumes because otherwise industry would not be interested, of course. And we can change the porosity. So you can change micro porosity because of the design, and you can change porosity inside the fibers, which can have an effect on the transfer inside the fibers and the productivity. Now, the technique is based on micro extrusion. So we typically start from powders. We make a viscous paste out of it, and coupled with the 3D design, we do the extrusion. Then we tune the solidification process to arrive at the right properties for different applications in the group. And currently, I'm talking about catalysis. Now, I'm talking here for Carbio. So the project was already presented a few times. So we start actually from food waste, torrefaction, and gasification, then the Fischer-Tropsch, and that's actually where we are involved. And then you have the fuel production in the Fischer-Tropsch, and then the upgrading of the fuels by other partners. So we are just shaping the catalyst, and the technology is testing the catalyst in their reactor. Now, Fischer-Tropsch, as you know, it's highly exothermic. So that's why in industry, heat management is very essential. So they use multi-tubular fixed bed reactors, double column reactors, depending on the catalyst. Sometimes also microchannel fixed bed reactors. And in Carbio, we use a fixed bed multiple reactor with milli-channels. So the idea in the project was to have very fine channels because then you get a good mass transfer, a good heat transfer, because that's essential to avoid hotspots. And what we are focusing on is on these long chain parafilms. So we use the commercial cobalt-based catalyst because it's well researched, it's well known. We just transfer it to process intensified application. Now, for 3D printing this catalyst, there are two routes. You can try to direct and you can do indirect printing. And of course, first we tried the direct printing. So we bought the commercial catalyst, we milled it, did the paste preparation, printing, and thermal treatment. But as you can see, the conversion was very low just because of issues during heat treatment. So you form essentially a cobalt spinel with alumina support, and you deactivate the complete thing. So that's not good. So that's why we also tried the indirect route. Now with the indirect route, we start from commercial catalyst, we characterize it. So we checked, okay, what pore size is necessary, what's the composition. We did a little investigation to see if we would need other promoters, if we would see some side directions. And in the meantime, we developed our 3D printed alumina support, which is also the base for this catalyst. So we did the alumina selection because we need the right precursors to arrive at the right surface properties. We did the rheology optimization, the binder selection, calcination optimization, to arrive actually at similar textural properties of the commercial catalyst. Then we did a design experiment for the cobalt loan. So we used incipient lattice impregnation because that's the easiest one. And in the end, if you can see at the TPR profile, we have a better reducibility than, of course, the deactivated one, and also better reactor performance. Now, we also try to develop further our own technology. In the project, we were working with 600 micrometer fibers, but because for process intensification, it can be also interesting to work with very small channels. We push the technology to go to even finer features. So recently, we were able to develop materials with 200 micron fibers to have an even higher geometric surface area, higher activity, and then reduced diffusion limitations. So of course, that's very important if you want to go to 4 millimeter vectors, which that's actually the size that Technalia is currently using our materials with. So starting from 600 micron fibers, you go to 400 micron fibers, you see, yeah, you cannot use the catalyst in that case. So we really had to develop our process to enhance our process to go to these fine features for dev tests. Now, of course, we also have challenges. So one of the challenges that we had was the selectivity to methane. So we got a decent conversion, decent liquid yield, but there was methane production quite a lot actually. And if you have the cobalt impregnated catalyst calcined, it's a black catalyst. Now, ruthenium, when you impregnate it on a black catalyst, you don't see where ruthenium is. But essentially in STEM, we saw that, okay, ruthenium was not homogeneously distributed. And in catalyst community, it's quite well known that ruthenium has issues sometimes with wettability. So what we did was we tried some additives, we tried different methods of impregnation of the ruthenium aspect. And in the end, we optimized it. So you could see that, okay, in the end, you don't see any ruthenium clusters anymore, which show that ruthenium is completely incorporated in the catalyst homogeneously. With these tests, with these fine features, we achieved up to 100% conversion, which is really bad because we produce a lot of water, which can also be deactivating the catalyst. But okay, that's out of our hands for the moment. But in the end, okay, we said, okay, the catalyst is fine. We have a good ruthenium cobalt interaction. We have a good conversion. So, okay, we can go to the upscale printing for the reactors. That's a higher scale. Now, what's also very important when you look at upscaling is, okay, you need to calcine the catalyst. Calcining one piece is relatively easy. But if you have to calcine 150 pieces, the furnace homogeneity, and especially when the reducibility is very sensitive to the calcination temperature, is also something to really take a look at, and it's often overlooked. So you could see that we have a very narrow calcination window which we could use, because if you go too high, you have the deactivation because of the spinel formation. And if you go too low, you don't have the spillover of the hydrogen because ruthenium cobalt interaction is not happening. So there is a really narrow window. So we had to do the optimization of that and finally to do the production. So in the meantime, we upscaled the printing. We printed up, yeah, more than 150 monoliths in the reactor. We did the cobalt impregnation, ruthenium impregnation. We checked for every batch the TPR profile of some samples to see if we still made the same catalyst. And you can see on the right the monoliths which were produced and which were sent in the end to Technalia for testing. And currently we are waiting for results. I'm very looking forward to them. So let's see later. So to conclude the presentation, so yeah, direct printing is not always the best route. We could also optimize it a little bit, but it looked also very interesting to push the technology and to go with indirect route. We optimized all the parameters in producing this catalyst. We were able to push geometric surface area close to 10,000 square meters per cubic meter, which is very high, which is also very interesting for other applications where fine features can be used. We scale the printing process and we're awaiting the results of the scaled reactor tests. And of course, yeah, we're looking forward for new collaboration opportunities to further push the technology for other materials, other applications, and so on. So with this, I would like to thank my colleagues in the project, my colleagues at Vito, and you for your attention. Thank you very much.
Shiraz, we have time for a couple of questions.
Yeah, if I understood correctly, when you build the instruction for the monolith, are you using some kind of binder or so? Or okay, so how are these binders stable? How stable are they in contact with the liquids from the fission tops?
Yeah. So essentially, what we did with alumina, what we typically try to do for catalysis is develop a binder that becomes a catalyst in itself. So what we did with this alumina is we used a boehmite binder. And this boehmite forms also gum alumina when calcined. So you essentially have a pure gum alumina structure in. Yeah.
And when you go to some other, like let's say more fragile samples like MOFs, how does it work?
Yes.
Can you still build a monolith out of it?
Yes, sure. But then you have to select a binder which is suitable for the application. So what we've done with MOFs, it's also what our group, other group at Vito is doing, is using, like, let's say, phase separation to form a binder that is unstable under the solvent conditions used in the reaction. That's an option that you can do, because you have to, of course, avoid that the MOF is deactivated because of pore blockage with the binder and things like that. So, but typically we investigate what's possible. So that's the first step in optimization. Is okay, test on paste what binders can be used without losing activity. And when we find something like that, then we can go to the 3D printing part.
Thank you.
Have you never applied this technique to the production of conductive materials?
Yes.
Yeah.
Yeah, we have printed titania, copper, iron, stainless steel. Metal printing can also be done, but of course the calcination and especially the sintering is then very important. So for copper, we sinter under hydrogen atmosphere, for example. But we have some sample there.
Okay.
Yeah. So if you have any interest, please contact me. Sure.
Thank you.
Any other question for Iran? My question is there any cost estimate for the production compared to the conventional catalysis for future through?
Well, it's still underway, I think. Yeah, I don't know. Of course, you have to think, yeah, this very fine feature is very nice for publication and so on. But then the advantage with using it in a million reactor needs to be very high, because the cost of the catalyst is, of course, also very high, because it takes a lot of time to produce. But for really bulk product, it can be very interesting, as also BASF is building the pilot plant. So for very cheap reactions, I think sulfuric acid production, they're currently using a 3D printed catalyst, and it's economically viable to do it. But of course, the feature size is then very important for the throughput. I think with that, they use, like, let's say 800 micron 1 millimeter feature size, and then you can have real productivity going out. But for the small features, parallelization is very important, and that's something that we are still actively looking at. So
thank you. Last question.
Sorry.
Sure.
I cannot wait. So I missed the first part of the presentation. I don't know how you introduce the catalyst. I mean, introduce the catalyst while in the ink that you use for the printing of the.
So essentially, I said, okay, we try to do it first, but then with the heat treatment, you can deactivate it, and that's what we did. So in the end, we reproduced the catalyst. So we printed the support, and then the recipient ran an impregnation of the two solutions to arrive at the catalyst.
Do you see any drawback in the impregnation part of the catalyst? I mean, when you upscale for a bigger monolith, because now you are working with small one, but once you have, like, I don't know, 2 meter monolith, how are you going to do the impregnation and calcination?
Yes. I think it makes little sense to make a monolith of 2 meters. I think then using a back bed makes much more sense for a productivity standpoint.
Okay.
So then there would not be an issue anymore. But used incipient wet impregnation. You can also do wet impregnation if you want to. So that could be a way to solve the problem. So I don't think there's a lot of issues.
Thank you.
Thank you. Let's join hands and Now it's time for the final presentation from Susanne Slinger on paradigm computation, modeling of separation of flue gas components.
Yes. Yes, thank you very much. Thank you for staying. It's almost the end of the session. I guess you have to get through me first. I am a PhD student here at TUE, and I will be telling you something about the work we've been doing within the Superfall project. It deals with the predictive computational modeling for the separation of flue gas components. So, of course, flue gas is a complex mixture. It has many different components, and it contains, for a large part, nitrogen, then NOx compounds, which are pollutants, and of course, flue gases are a large part of carbon emissions. So we would like to capture this carbon CO2 from the flue gas. And within Superfall, we propose to do this with a MOF, TAMOF1. There were already a couple of presentations on this MOF. And I'll be dealing with some of the modeling work we've been doing on this particular MOF. Some of the basic properties, it's basically very stable, which is good. It doesn't have any critical raw materials. And it absorbs CO2 selective over nitrogen. So how can modeling contribute in general, but also in this project? It can help in understanding absorption mechanisms in MOFs. We can also screen very fast and efficient because computations are generally cheaper than experiments. So we can screen many different operating conditions and many compounds that might be difficult to use in a lab or just in general cost a lot of time. So the specific goals of our project in this work is to develop a model that can predict the absorption in TAMOF1. Then we investigate TAMOF1 for flue gas separation and also assess the effect of impurities, so NOx compounds, on the separation. So to correctly model absorption and then later separation in MOFs, we use first for absorption Monte Carlo simulations. These are molecular simulations. In our case, we fix the materials, the MOF and the adsorbates, and make them rigid. In our case, the MOF is a very rigid structure, so that works. And then we treat the system classically. So we only consider electrostatics and van der Waals interactions. And the van der Waals interactions we describe with Lennard-Jones potentials, from which the parameters we get from existing literature force fields that basically are able to reproduce bulk properties. And then we assume that also works when we start mixing it. Of course, this has to be validated. And then separation. For the separation in our project, we used numerical modeling. So we didn't do any molecular simulations anymore. We used the code Rutura, a software package that is based on the ideal absorption solution theory. And it takes as inputs isotherms, either computed or experiment. We fit them, and then we can get equilibrium absorption isotherms of mixtures, but also breakthrough curve predictions. And for these breakthrough curve predictions especially, we don't need a lot of parameters. So we need the isotherms and then some bad parameters, column length, void fraction, and mass transfer coefficients of the components. Now going back first to pure absorption, we've modeled the absorption isotherms with the Monte Carlo simulations. On the left, these are for CO2 and on the right for nitrogen at 4 different temperatures. So the colored lines are simulations, and then we have the experiments there as well. And as you can see, the CO2 isotherms are very accurately reproduced. And for nitrogen, they're also very close. We estimate them in simulations a little bit, but because the N2 absorption is very low, the difference between the simulation and experiments is also low. So our force field is able to accurately model absorption isotherms. And this is great because we basically treat the whole system classically. So these simulations are fast and cheap. Then looking more closely into the Monte Carlo simulations, we can get more parameters out of them. For instance, the heat of absorption that is plotted on the right for both CO2 and nitrogen again. And when we now start to compare the CO2 absorption versus the nitrogen, we see that, okay, CO2 has a higher loadings, absorbed loadings. It's also a higher heat of absorption, but it also shows a different mechanism. The heat of absorption of CO2 first decreases, and there's also a plateau in the isotherm. Well, when we look, we have visualizations of the simulation, so we can clearly see where the CO2 goes in the framework. And what we found is that there are these the copper 2+ atoms in the MOF. They are aligned in triangles. So yeah, it's a bit difficult to see in this MOF, but they're triangles, and they provide very confined space in the MOF with an electrostatic potential that is very favorable for CO2 to preferentially absorb. And we can see this also if you look at a simulation at a low pressure, so 10 kilopascal, is that the CO2 density was mainly located in these binding pockets. And then at high pressure, the rest of the core had also filled up with CO2. We did some additional DFT calculations to further look at, okay, what is exactly geometry of CO2. And there we actually see indeed the CO2 goes to these copper atoms aligned in a triangle, and then it has an interaction energy of 50 kilojoule per mole. And also nice to note that the classical force field very closely matches the energy retrieved from the classical simulation. From the quantum calculation. So the copper 2+ binding sites provide the preferential absorption sites for CO2. Then we move on to the separation. So out the isotherms, they were put into a numerical model, and now we can very quickly, and this is within a second, calculate different metrics that are used to judge a separation performance of a particular adsorbent. And a metric that's very often used is the selectivity, which is here on the left. I do it for the entire pressure range for several different CO2 concentrations in nitrogen. And we see that TAMOF has very high selectivity. If we go to very low pressures or quite high pressure, then selectivity starts to increase. Well, at low pressures, it really blows up. This is due to the fact that there's so little nitrogen in my system. I divide by a very small number, so I get a very large selectivity, but it's basically an inflated number. So in the past years, I have now seen some papers that report a TSN number. It's called the trade-off of selectivity and uptake. It uses the log of the selectivity and then also multiplies it by the actual uptake of CO2. And this is then seen as kind of representing the fact that in general, in a separation, you want good selectivity, but still you need to capture some of the actual product that you want to capture. So I've also computed this, and there's not much to compare to yet. There are a couple of papers now, mostly with other types of separations. But these also seem to be quite promising for this. But just to say that complementing metrics gives a more complete view of separation performance. Then the dynamic, the breakthrough curve modeling. So here we've performed simulations of breakthrough curves of CO2 in helium for different pressures, temperatures, gas velocities, pressure. And the experiments are shown on the bottom and the simulation on the right. So this was done with our numerical software model. we could very accurately reproduce experimental trends, and also most of the time the time at which the inlet concentration was again reached. Where we still can improve is the width of the mass transfer zone, so the point at which the CO2 starts to break through, and the shape of the curve. We are looking into multiple factors. Right now, the model we use is still quite simple, so it uses a few assumptions. One of the most important ones, I guess, for CO2 is that it's an isothermal model that we used, and CO2 adsorption generates. So this can actually have quite a large effect. We're now working on a second part of a new part of the code that doesn't incorporate the heat transfer. Initial results are really promising, especially for CO2. It does really improve a lot, but it's not ready yet, so we're still working on that. This was CO2 in helium, and we were actually very happy with this, that we can match the trends and at least roughly the times breakthrough. So now we also wanted to test if we could actually compare this to CO2 nitrogen separation. Yes, so this is the plotted dashed line is the simulation, and the solid is the experiment. It's both for CO2. The nitrogen in both cases elutes immediately. Well, at least we have the fact that we can separate CO2 from nitrogen, correct? But the breakthrough time now it was very off. And we were very surprised because at first we thought, oh, our model works well. And then it didn't. So what we did is all the parameters we inputted in our model, we basically tested the sensitivity of our model to fluctuations of this. So the experiments used the parameters here shown in the yellow bands. And what we then did is we kept all the parameters fixed and varied one. It's called, I think, sometimes a local sensitivity analysis. To basically see, okay, how robust is our model to fluctuations? And what we especially found that in comparison to the validation I showed here, the used flow rate in this experiment was a lot lower. And we're now in a regime where, as you can see, if the flow rate changes a bit, our breakthrough time will changes a lot. So not to say that our model is wrong. I mean, this is just the math of how it is. But at this conditions, our model is very sensitive to fluctuations, which could explain the large difference. So I think it's also a good point to make with any simulation or modeling you do. It's also to test not only how well it works for a particular case, but also how sensitive it is to certain variations. Then a final point, the impurities. I also computed the isotherms of a lot of impurities that can be present in flue gas. I won't go over all of them. Yeah, there were three again with the same mechanism as carbon dioxide. And then we have another. But what I use these isotherms for is we got the question, do NOx as in particular, so NO and NO2, have an effect in the concentrations that are present generally in flue gas on the separation. So we did a simulation, and what we said to experimental friends, we said, well, in our stuff, the NO and NO2 comes out immediately. So you don't need to separate the nitrogen, you don't need to separate the NOx from the CO2 in a later stage. And then this was later validated by the experimental collaborator. So the NO and the NO2 leave indeed immediately. So this was one point where we basically could make a prediction. We said we think that the NOx won't have an effect. This turned out to be true, and it was very helpful to the project. So it was very nice. So to conclude, our model can accurately reproduce adsorption. We can also calculate separation properties and say something about mechanisms. the big point that we're still working on is to improve the agreement with experimental breakthroughs by including more parameters in our model. Hopefully, we need to do it. So with that, I reach the end. So thank you very much.
Thank you, Susanna. We have time for a couple of questions, please.
Thank you for a nice presentation. I'm wondering, so you did the modeling of experimental data of your partners, right? Was this experimental data, was it on a powder or on pellets or on shaped material or?
Yeah, so in comparison with the breakthrough, I guess, yes. So the plots I've showed are with powder. Now the experimental people have made the pellets, and we are now doing also the comparison with the pellets. Probably your saturation loading is lower, or it is lower with the pellets in 1 kilogram. So we'll probably do a conversion factor on the isotherms and then model it like that. Yeah.
Maybe also, maybe you did already, but maybe it's also good to take into account kinetics. Because kinetics can also depend on the flow rate.
Yeah.
Maybe that's why you have a discrepancy between the models and what you also have seen before when we tried to do breakthrough on powder. Check kinetics on powder is that powder bed itself also influences the kinetics of the uptake, depending on the size of the bed, because you have diffusion to the surface and diffusion through the material.
Yeah.
So if you do some experiments and you see differences in breakthrough curves, it could also be due to that. So maybe some things to think.
Yeah. That's a good point.
Thank you. Any other question?
So, yes, just one thing. So from the ITO solution that you have analyzed, so basically the only impurity that can give a problem is the SO2, right?
Yeah, well, yes. So this is all. Oh wait, this was further on in my presentation. The absorption isotherms, these are all pure, like 100% SO2. So yes, when I get SO2 comparatively to CO2, yes, it gives me a problem. But you also, it matters how much SO2.
Yeah, of course. Yeah.
Yeah.
Thank you. And may I ask if, for example, you have humidity definitely in the flue gas, how that can affect the process?
Yeah, so we have done some things from this. So this MOF absorbs water well. It's with every MOF that absorbs CO2 well. So if you get high relative humidity, you get competition with the CO2 for sure.
Does that affect also how it will basically react with the nitrogen compound N1 and N2? For example, if you have moisture trapped in the MOF, then the solubility of the nitrogen compound in the water also should be considered.
Yeah, so I haven't done any work on this. Yeah, I'm not sure if we've done anything with water and NOx present yet.
Okay.
Okay.
We have done experiments.
Okay.
I don't think the computation.
No.
And from experiments.
The problem, if you have water and this nitrogen or sulfuric acid, the problem is that you generate the acids. It's not that you are passing water and NO2, you are generating nitric acid or sulfuric acid. And this typically is not good, not for the MOF, not for anything. So typically for application, we remove water. If there are the rest of these gases, they are not a problem. But the mixture generates the acids that are a problem for everything. This is what we have experimented. So the NOx is no problem, but if there's humidity in combination, then it's a problem for the long-term stability and the performance. We get some permanent damage. It's not completely destroyed, but there are areas of the material that are decomposing.
Thank you so much, Susanna, for a nice presentation. And with that, this is the end of the session. So we go to the main room. Yes, the main room, please.